We are, I think we're all lucky that Pooyan Jamshidi is, taking this class. He's, among the brightest researchers that we have in our department. He has, the quality of his work really shows the number of awards that he has won, for his papers, and how influential they are. Now, I have a little hard time exactly pin down his area, but I mean, he's done software engineering, I think systems and AI, in AI, particularly causal AI related work. And I think, he's had well-funded research and, he's guided students effectively. And, let's see if we understand how quality research can be done, as well as very interesting topic here. So thank you, Pooyan. Awesome to you.
Thank you so much, Amit. Let's start. So today we'll be talking about a line of work. So it is related to three recent papers from brilliant students who have worked with me in the past couple of years. So it's three papers that have been recently published in my group, and I'm going to connect them to this talk and contextualize things also for some of you who are not familiar with some of the underlying concepts. And during the presentation, whenever you have any question, please feel free to stop and you ask your question. I know that some of the students, some of the audience here basically are familiar with some of this work, which is great.
Yeah, around that, so that we can at least get your voice well. But
okay. But I know that probably some of you are not too much familiar with some of the concepts I'm presenting today. So I will provide some background for those who are not familiar, and I'll be spending more time on understanding the problem that the students, authors of these three papers, work on and developed, and connect them in a way so you can understand why I'm calling a line of work instead of just one paper. Now it's not going to the next slide. Can you help me? Okay. So it's probably slow. So I start off by giving you some overview. And the overview, you can think about it as like, of course, again, some of you who are not familiar with the context, giving you some discussion point or question, if you have, about significance of ML inference, especially at the scale. And it's very simple. So the most popular systems that you have been using these days, most of you, ChatGPT, is a good example of this type of system that I'm talking about, right? ML inference pipelines. So why it matters? The key points that I would like to highlight here is that where is ChatGPT? The actual thing is located in some huge data centers across the world, right? Most servers, I know that it is located in the US, but some of the servers that host in ChatGPT, this huge system, is located all over the world, right? In the data center that OpenAI is using. Okay, one system, many locations, and there are many other typical systems like ChatGPT and so on at different scale, mostly smaller because now ChatGPT and LLMs consume most resources in these data centers, which basically, I mean, recent reports mentioned that 90% of the resources is consumed by ML inference, which, by the way, was not like that even like a couple of years ago. Okay, so this is a very recent event. When I was doing my PhD, it was at the beginning of cloud computing and many advancements in building data centers that host those type of applications because it was at the beginning of this new era of AI. Back then was mostly started by vision tasks. Now is like multimodal tasks, not only vision, but text and other modalities. I'm not getting at history of this evolution, but hopefully now you understand the context of this presentation, okay? And more importantly, I mean, even in the context of LLM, like the evolution in the past 2 years, just 2 years, came from like type of NLP systems with single node. So this type of multi-node composed systems, right? Where LLM is composed with search engines and other components to do the amazing tasks that you use in ChatGPT interface. The underlying architecture of ChatGPT at the high level looks like that. So what is the core challenge I would like to highlight here? I start with this core challenge because it is super important. And if you understand this core challenge, that's about the takeaway I want you to have for this talk. And the core challenge is very simple, is basically a trade-off between multiple objectives. Very simple, right? What are these objectives? Accuracy, cost, and latency. 3 objectives. Okay. Again, this is one particular problem, very specific, but I would like to emphasize that you can take away the thing that you can take away from this talk. You can formulate many other relevant problems in this way. And that's, I would like you to think about it throughout this presentation. But let's get back to this very specific line of work, right? So ML inference that, again, I emphasize as an example, ChatGPT, but overall, like there are many other systems. Like think about it as type of systems that have some strict requirements, right? What are these requirements specifically I want to highlight? One of them is they have to be responsive, otherwise you are not using ChatGPT if it is slow. That's about it. It has to be cost efficient too, because OpenAI has like good amount of money, but it's limited amount of money. And it has to be accurate, otherwise you are not using it. Hopefully it is clear. More importantly, there are trade-offs between these objectives. Although these are strict objectives, like for example, we want to reduce the cost. We want to reduce the latency between your communication with ChatGPT. Think about minimization of those individual objectives. But these objectives are essentially in this context are conflicting, meaning that you cannot individually focus on one objective and just considering reducing that. Imagine OpenAI just considering cost, minimizing their cost. None of us would have been using this, right? One server on their backend, like the company probably would have been sufficient for their own use, not million of us, right? So that's about it, and until you get it. Also, not all of us using ChatGPT at night time. Maybe some of us. Mostly we are using it during daytime, right? So the number of requests hitting the ChatGPT backend server would change over time. And you can consider it as a dynamic change. We can visualize it like this, that sometimes during the day, number of requests is huge. Night is not zero, is less requests hitting the server, right? Simple as that. Now, very important thing. I would like to emphasize that the number of servers that ChatGPT requires, again, as an example, if they allocated a fixed number of servers, right? Like even like under fixed number of servers, meaning that trivial number, okay, fixed, this is not good enough. Like this is a trivial, easy solution, like 100 server, but because the workload is changing, there could be some issues happen. During daytime, when many of us using it, it becomes slow because, I mean, this amount is not sufficient to provision enough resources for this number of requests that is in the background. I mean, people found some fancy word like under provisioning, but you got it. And during nighttime, this amount of resources is higher than these requests that is hitting again, meaning that they are paying more cost for hosting ChatGPT than it is needed, right? So this a simple trivial n number of servers, doesn't matter what is n, but fixed is easy solution, but not good enough. And you understood why it's not good enough. Again, people in systems community where I primarily belong, call it over provisioning for like nighttime, meaning that provisioning more servers for resources than it is needed, or under provisioning for daytime usage, which is not enough. Okay, that's how we can think about these fancy terminologies. I mean, I mentioned ChatGPT, but I would like to highlight that there are other type of systems which has similar flavor, meaning that they have multiple components. And this example, one of these systems that, for example, you can consider it as some data coming from different sensors for, let's say, tracking the cars in Colombia. Go to video encoder, some fancy components, and detect, like DMV detect what car is where and etc. Right? And some other downstream component that does some other tasks. And essentially doing some analytics for controlling the traffic. I mean, Colombia is very small, doesn't need these fancy systems, but huge cities like New York require this type of system, and they use it. And this is a good example again. If you want to have better understanding, you can look up this relevant paper from one of my former students, Tahria, who has worked on Williams' paper, John. But I'm not going to talk about that. This talk is different. Get back to the example. For this example, a trivial allocation is that allocating one server for the whole system pipeline end to end, which again, for this system, very similar way, the number of cars that appear during daytime is way higher in any city than nighttime, right? Same thing, right? And same type of allocation, naive allocation all the time, which is sometimes at daytime is not enough, at nighttime is more than. So again, similar way. Second example, for giving you a chance to generalize. And again, same issues that I highlighted. Another thing that makes this problem non-trivial. Now I'm getting more of giving you some, highlighting some challenges that why this problem of provisioning right amount of resources when it is needed, like when the number of requests is going high, allocating more servers, and when nighttime going down, but getting rid of servers that they acquired so they can reduce the cost, right? And that's why, because it affects the cost. I mean, from the cost perspective, but it has some other dimension, as I mentioned, it also affects the latency as they have more servers or less servers over time. So, and I will make this super clear later on, but this type of system for resource allocation, the way how we formulate it, or some other also work also formulate this way, it has many different state space. That the number of states in this formulation is huge, exponentially huge. And through example, we understand why it is exponentially huge. And you can think about it as more than number of atoms in the universe in most of these formulations. So we started by understanding these challenges, right? And another aspect of which particularly belong to ML inference, which might not necessarily be relevant to some other systems where are not ML specific, because like few years back, it was not the case that all systems are ML specific. And even these days, like many relevant systems, they have some non-ML components. Okay? It's not the case that everything is ML enabled or deep learning enabled. There are many computer systems that have many components that are not necessarily ML enabled. Okay, don't forget about that. So this talk specifically is about ML type of systems or type of computer systems where they have several ML components. Okay? And most relevant systems, like even like ChatGPT, has some non-ML component like search that I mentioned, right? This is not the case that ChatGPT only has neural network transformer. It is composed with search. Okay. Otherwise, like they couldn't give you the result that some people interpret it as intelligent. And some of those components avoid the hallucination, many hallucinations that the only ML component produce, right? And that's why they are there for this purpose. I mean, some of them. So back to this, in ML pipelines, one thing which is relevant is that you can use like different different type of neural network, for example, in particular, make it clear later on why different variants. We can think about it in a very naive way that, like, I mean, ResNet is like, I mean, back then, 30 years ago, before LLMs, ResNet was popular as vision transformers these days are. Then I will see by PhD. But ResNet, we can think about it as having a smaller version of ResNet, and we call it version 18 that has 18 layers, and 152 that has more layers, right? For a very simple task of classification, obviously, a smaller model may make more errors in predicting what is in the image on average. And typically, on average, bigger models, we expect that they are more accurate, meaning that in their prediction, they mostly, I mean, they make error, but they make less of errors overall, on average again. And you can think about it, this is one example that maybe the smaller ones make error, or bigger ones do not in this case. And which one do you think? Pickle alpha, we have seen this is a dog that is painted as target. Pickle alpha. So essentially, again, back to this, that again, this was trivial annotation. This basically axis, the y-axis, pointing to accuracy. I mean, this was resource, but pointing to another dimension. So to clarify this, meaning that the accuracy of some of the components, if we switch between different model variants, would vary over time. Similarly to like latency, for example. So, it's jumping around automatically. So basically, a similar other brilliant research work that all of you are doing, most of you, our work is built on top of shoulder of giants. I mean, every single research, if it is solid, has built on prior work. Okay, don't forget that. And these are some of directly relevant prior work that we directly compared our result with, and I wanted to acknowledge them. And I will clarify and later on when I'm showing some of the results. So now, hopefully you've got some understanding of challenges that makes this problem that we have some solutions non-trivial, right? And that's why I'm saying that these are, again, brilliant work that my student has have published and basically developed and experimented with and compared with and submitted and got review, some of them rejected and finally got accepted. Long process, but we get into these solutions that I would like to highlight. And these are the three specific publications that I'm going to talk about. Two of them has been published at Neuroanalysis and one IPA published at JCS, which is like solid systems journal. But these papers that I'm going to present, I mean, I should finish it soon, the presentation. Emphasizing that I wanted to highlight the problem. For me, understanding problem matters much more than the solution that I'm presenting. As long as you understand the problem well, and you can generalize it to some other relevant problem, that is good enough takeaway for you for any talk. And my style of presentation to be like that. Why are interconnected and relevant and not very separate, and why I mentioned that line of work, not really totally different for, is that these three work somehow at the abstract level from like at least mathematics perspective, solving the same type of problem with different variations, okay? And I will clarify it when I'm presenting them. Is one of them solving a multi-objective optimization with some known unknown concept, simple as that. And those of you who are familiar with math and theory, particular calculus, can get it, what I say. What are the variations? Basically, here, same problem for one node. I mean, it's not ChatGPT style. One node, one model, one task that has a model inside the model. So very simple type of system you can build with this, like this assumption when you have one model server and solving one task, let's say classification. Type of system we can build. I mean, for example, you can build an app that classify that show when you show the plant, tell you what plant it is. You can develop like this type of app using one model sitting on your phone. And this is a solution for that type of systems. IPA is addressing a solution that is more relevant for ChatGPT-like systems. I mean, yeah, I'm not claiming that it directly evaluated with ChatGPT, but we have evaluation of the type of system similar to ChatGPT scale. ChatGPT architecture, other scope. I will clarify that later on. And the last solution, a sponge, is basically and I cannot finish and talk more about detail about sponge, but I would like to highlight the sponge is like similar to IPA, but with addressing in the context of the type of systems that uncertainty, such as network bandwidth, come into place for the type of system that typically are deployed on phones, right? And this sponge is one relevant solution for this type of system. So I start off with the first one, Inf adapter, and the direct prior work that we compare our result with is this paper. Yeah, good paper. It's not our paper. Paper. Quickly clarifying what is the difference. You can think about it, again, I mentioned one model server hosting or like for solving one task classification. The same like ResNet, you can have like different variant of ResNet, doing this simple classification of like classifying different flowers. Or different animals, right? Whatever you can consider. Again, this is trivial type of system because it has only one node. The difference between our and model switching paper is that like for resource allocation, we considered allocating multiple variants instead of just switching between different variants. Model switching paper switches between different variants of the same style of the same architecture. For example, their solution switch between like sometimes uses ResNet 152, which is bigger for classifying maybe type of animals which have more variations. And ResNet 18 sometimes and switch back to ResNet 18 because it is smaller. Maybe at that time, like the number of requests to the system has increased, right? Maybe more of us were using this, like classifying what is the flow, right? What is value. Because again, back to changes in dynamic workload that I started with, the challenge of dynamic workloads. And we have a very good experimental result to motivate why our solution is superior to this. And this is the one angle of looking at that reason. How we can interpret it. Again, 152, same. On the y-axis, we have throughput. Okay, and also these different colors showing different number of resource allocation, right? This color shows that 8 CPU core has been used for basically hosting this system, and the black ones shows more resources. Okay, 20 CPU cores. 20 CPU core is larger resource, and you need to pay more to acquire these resources. 8 is like less resource and obviously less expensive. Okay. So what we are saying is that if the system switch between different variation, or we call it specifically in the paper variants, model variant, with different resources, the throughput obviously varies, right? Like at the time, consider this blue bar. So with a smaller model, you can do more inference. This axis showing the number of inference. Throughput is like number of inference, number of time you can do the task, execute the task per unit of time, right? That's how you define throughput. So one way of looking at it is that different variant, with a smaller one, you can do more of this execution. Is somehow intuitive, right? The smaller one because it consumes less resources, right? So you can do more because the task is needing less resources for the job that it is doing. And again, this number of execution is one angle, one objective, right? And I'll discuss another objective why then become more interesting. And when we give it more resources, also same thing. But specifically, now consider these two. Now forget about like these two, consider these two. What they are saying, like I'm highlighting this because they basically have equal throughput, meaning that we can use the smaller models and less resources, getting the same number of tasks executed, comparing with bigger model, more resources, right? So smaller model, less resources, you can do the same number of time execution as bigger model, more resources. What does it mean? Meaning that you can basically switch when it is relevant for resource allocation, which is super important, right? But the important thing, like this is number of time execution tasks without considering the quality of the work, which is accuracy. Because then when you consider accuracy, then you can, by this switching, obviously it affects accuracy, right? So you can consider when the number of requests goes up, what you can do is that you switch back to the smaller model. This is what model switching paper has been doing, right? Now, this is the direct comparison between the model switching, because this insight that we experimentally shown in the previous slide is true for both work, right? Doesn't matter, like model switching or our paper. Comparison between these two in particular give us also some insights. again, I would like to highlight that in model switching, they switch between different, like from 150 to 152 at a time. So at any time when you look at the system, they use only one model variant at any time when you look at the system. Us, we said, why? But we can maybe use multiple variants, which is important when you consider accuracy. And this is simple to understand because before, I mean, this is showing basically, I will get back to this to clarify, but I would like to go back to this, that again, this visualization helps. And again, model switching paper at any snapshot of the time, when you look at it, is offering one variant to this box, to this model set. We, in our work, we decided to keep track of like multiple variants because if we have a system that at any time look at the system, sometime, I mean, it's not the case that ResNet only has two variants. You can like create this, like you can chop it off and like you can create n number of variants, right? And that's the key point. Can have like way smaller model for our watch. You can have way bigger model for big server, right? Doing the same task of classification. Since we have this variability in resources, this allows us a system flavor, right? And that's why it is super important, and why our work basically is novel, emphasizing that the key point is that when we use multiple variants, we take advantage of some important lesson from a statistic, right? Get back to smaller model, lower accuracy, bigger model, higher accuracy. What the statistics tell us if you have n number of model variants? Any insights? Anyone of you want to make it? It's very simple. It's again, everything is math, it's statistics. Is consider accuracy, like imagine these numbers. These numbers, right? What this tell us? Present 50 is like on average, it's around 77 accurate on like image methods. Image method is yet another data set. Back to time set with size data sets, which we can expect you to evaluate the work. And these are like top 1 and top 5, but consider it actually it doesn't matter. And if bigger model, you see that it is more accurate, right? On the same task. And again, I'd like to emphasize that it is not only two variants, you can consider many variants here. And when you have a system that at any time uses multiple variants, you can take advantage of average. Simple as that. right? Very simple statistics, but very intuitive. And this gives you a variability space, which is like more interesting, more granular than trivially just using one variant of the model. And that's why it is beautiful. Our solution is like, I'm proud of this work. Hopefully you got it, and these results become also trivial. There are some fancy formulation. Probably you don't have much time. How much more time do you have, Amit?
We have 10 more minutes.
Okay. Again, wanted you to understand the problem. That was the only thing that matters. Those of you who are interested, you can talk about math. And these are passionate in math, which are easy to understand. You can also read the paper for this. Let's review this quickly. This is like we formulated as a maximization. This is again multi-objective optimization. And we transform it to single objective very easily. Is maximizing average accuracy with some penalty for resources and loading costs, meaning that when you basically load variance, it has cost because it takes time to load it up, right? And with some constraint over latency and resource usage, etc. This constraint, for example, to like specify or enforce that this multi-objective optimization, where we transform it to a single objective to make it easier to solve, support the incoming workload of the system, because we want to have enough resources at any time to support this incoming workload. And we enforce this way by this constraint that it has to guarantee end-to-end latency. We talked about this, but there are Saeed in particular developed this system, the first author of IPA. Mehran actually primarily wrote the code, but Saeed helped a lot. The first author of the IPA board. They did the monitoring to keep track of the workload, seeing how many requests varies. The adapter is the controller that allocate the resources for the system, and some fancy API. For those of you who are interested in system development, you can look it up, detailed in the paper. And this controller essentially the way how you can think about it, like by solving that optimization problem that I just presented with some solver, again some solver. Right? Use Groovy, but it's the same thing for those who have used solver for solving mathematical formulations. And decide, what subset of these variants that we created for this experiment to become that minimize, that optimize the problem, the multi-objective optimization formulation that we transform into single objective, basically optimize that, but also meet the constraints that we discussed in the problem formulation. Simple as that. So everything is very simple to understand with this formulation. And there are some fancy results. You can again look it up. Because I'm sure you understood the problem. Like now it becomes easy. But quickly, this is a synthetic workload pattern, some variations, again synthetic, right? Adopted from some Twitter workloads. I mean, synthetic in the sense that it is not like synthetic trivial, is one Twitter trace at some time ago is relevant, right? Relevant, I mean, evaluation, relevant, solid. And let's see. This is the workload. This is the P99 latency, okay? And we compare we compare our result with some existing like autoscaler solution. BPA is a like autoscaler on like many that has many systems. I know that is the resource allocation controlled by BPA autoscaler in data centers. So it is also very relevant. It's not a really trivial system. So we, like a student, created one version of BPA that only used one variant, like resident 152, and this is how it varies when you get hit by this number of requests in the workload. This is the variation in latency. So what does it mean? Meaning that we imagine, or we like imagine a relevant constraint that this is the latency that the system has to meet. Otherwise, everything goes up means that it violated this constraint. Okay, it violated. I mean, it can violate, and many computer systems violate the SLA service level agreement. Many of us also violate something, but we have to pay penalty and same thing, right? So the system has to pay some penalty for this violation. What does it mean? Like, we don't want to violate a lot, right? And whoever solution that violates less is winning. That's one interpretation. But this is like curve, this curve latency for VKA 15. A smaller model that has been controlled by the resource has been controlled by VPA. Again, it's not our solution. None of these is our solution. And this orange one is the third one, which is VPA 18. Again, a smaller model. And you can guess now why it is like lowering the latency here, because it's smaller, consume less resources, right? And that's why latency is lower, because less expensive. It's doing less of the task when request is switching the model server. So it's really why it's getting lower when we use a smaller model. You see that like the amount of violation is lower, obviously, right? When this search happens. And this search, why this workload is relevant? Because this type of searches, sudden searches in the workload is basically is relevant back to earlier slide that we discussed why like daytime more of us using ChatGPT, right? Same thing. MS Plus is still not us, model switching paper, plus because we also enhance it with some new component that do some prediction of like when it is here, predicting that the workload maybe is going higher, predicting, not exactly knowing, right? So we gave it some to have a fair comparison, because we also do prediction, to have a fair comparison with a similar solution. Again, I would like to emphasize this because it is important to do solid research and have fair comparison when you are comparing with the state of the art. And this is the result. So it's obviously doing, because I think that good work is doing better than this EPA on average, right? Less correlation. And this is us, right? This is if adapter when we have use a subset of models, right? What do you see here? Anything that you see interesting?
For a lot of applied, about matches MS plus, but then it seems like that spike might be a bit sharper, and I would assume it's been tuned to where it gets better accuracy than the MS plus.
Very good, very good. This is like, again, is not like, is like one initial experiment, right? It's still not the real experimental results for comparing all, right? And the intention of this paper was to understand what's going on when we have this capability of switching between a subset and only using one, and become like, and again back to this problem that this is a very simple problem. One node thing become relevant and interesting in IPA when we have a pipeline, multiple nodes, because then the search space become exponentially larger, and our solution using a subset of variants provide a much better result in this vast search space. Because here, like one node, like subset three, and like variation is not huge, it's like very small, but still showing some better result. When you look at the accuracy in particular, I mean, this is only latency, because like the interesting part is also like, again, this is multi-objectives. Like this is only latency. Like things become interesting when our promise of using a subset, I mean, comparing to the latency, we are doing the same as, I mean, MS plus. Same. I'm not saying that like we won in latency, and that was not a purpose. Back to the problem again, purpose was subset provide, emphasize that like a simple statistic of taking average accuracy, right? We expected to have better, showing up better when we compare in terms of accuracy, and that's the result showing up, right? If you look, and in particular look at other here, which one is us? It's adapter, right? This is not accuracy, it's accuracy loss, right? Meaning that lower better. Which one is better? Even on this trivial example. I mean, us, beating, but literally, yeah, not a big deal. I mean, with this result, you cannot like solve a ChatGPT type system, right? This is one node, like it's still not trivial, like for classifying tigers from, like classifying animals for flowers or interesting vision. These results could be useful, but not ChatGPT. Things also become interesting, not only latency, because again, it is multi-objective. Latency, one objective, previous slide, accuracy, another objective. This is cost. Look at the cost. Which one has a lower cost? Because we want to reduce the amount of cost of allocating resources. I mean, obviously, when one variant is smallest model, this is the lowest possible cost, right? This is obvious because we use a subset, right? What was important was that, like, I mean, these oranges, these VPAs are lost in the two other objectives we started badly. Our component was MS Plus, right? Who is winning it? I mean, it's still comparable, nobody's winning. Good enough to be comparable because we won in previous accuracy. That was important, right? You do not need to win in all objectives at the same time, and you have a multi-objective problem. That's the takeaway I want you to have. There are more slides. I'm sharing this slide, and you can find these 3 papers, read them, but I'm sure that you can follow and understand fully by this discussion these 3 papers. One thing I would like to highlight before we finish, let me mention this, that two teams also works on some extension of these 3 lines of work, in particular IPA, which is built based on the insight that we discussed. For pipeline, which is very interesting problem. These are the 3 students in one team that took my 585 class, ML systems class, where we study real world ML system. And this is also another team. These 2 have done great. And you can talk with them if you're interested. Let me finish up with this slide. And basically, this is just the last slide. I started off by discussing some well pipeline few examples we had. And in this context, basically, we have multiple objectives, which is controlled by some variation of resources, etc. I mean, when you read the IPA paper, you see, for example, batching. We already discussed one or two variation dimension, but the batching and the scaling also. I mean, we also discussed the scaling. Batching is more relevant to like pipeline. When you have the pipeline in particular, same thing. You could have more variation of this. Like one brilliant student in my group here is doing way of from causality perspective. But again, these are like the mathematical perspectives. But with like more relevant type of systems, which do involve some uncertainty and some other dimensions, which makes it super exciting and like obviously way harder to develop systems to do this type of task. And causality aspect are like very interesting aspect that allow us to look at some causal perspective of this formulation. and everything, I would like to emphasize this modern ML system and all type of computer systems these days have the same flavor, right? Not only ChatGPT. Robotic system, many computer systems, you can look at them from this perspective. And that's what I want you to take out from this talk. And thank you for your patience.
Such a wonderful, introduction to.
And
the
thank you,
work.
Amit, for
Yeah.
this
Oh,
opportunity.
thank you. And I really urge you to consider taking the kind of, the special courses that a faculty offers. His one will really be demanding, but then you'll learn a lot. So for, maybe before you, decide your research team, if you can take the course under the faculty you're considering working, you should do that. And even if you not, if you have that extra time and want to really get deeper into that, then take the courses by somebody like Pooyan. He's, I think he's going to really put you through the paces and really get you to understand something very, very well. So thank you very much. Really
My
appreciate it.
students here, Fatima and Abir,
Oh, they're there.
pleasure to talk with them. Hopefully they don't say bad things about me. But please talk with them and
No, I mean-
learn from their research. Thank you.
I'm sure, as demanding as you are, but you want the good result and they will succeed if they deliver.
I'm proud.
I'm
of
sure that there will be few who can't handle it, so that's okay. But you're lucky if you.
I'm lucky actually to work with these brilliant students.
Yeah, no, if the students are really dedicated and they want to get best out of you, then you're lucky, yes. But some people are not all that, they want, degree, not the learning. And that, to become an independent researcher is a totally next level of thing. To learn, go to the courses, get the grades, pass, comprehensive, that's not that hard. To be able to do what your advisor did immediately after your graduate, that's a high bar. And so,
I find like almost all of this work has been done by students. I wish I could be more involved. I
okay,
wish like I could be more helping them. I mean, life has challenges, but
oh, yeah, no,
I
that's
mean,
true.
I'm proud of their work. That's
Look, I mean, you're getting a good sense of what it is. From AI Institute in 2023, we had 100 publications. My own group had 42 in 1 year. Last year was more, I've not counted. And so, yes, you and I can't do everything that goes out at the level of detail and depth that we want.
I'm going to compare with Amit, like number of publications is order of magnitude lower, like few, every year. Few.
No, but at the end of the day,
It is like
number is not
big
important.
guy,
It's the
like
quality
very
that
small.
matters. It's the quality. Every paper you get out, if they are, more of them are hit, then that is far more important than getting many papers out and nobody care about. Now, thankfully, we get a lot of papers out, but a lot of people care about it. More than 13% of all my papers, there are more than 1,000, have more than 100 citations.
Yeah, that's a huge achievement.
So I think that's, for all it is not me, it's always, at this stage of our lives, it's always stewards. I am I got my PhD in 85 and I still managed to be relevant. It's very hard to be relevant after so many years and reinventing after so years. And even for him, he's now a full professor and so he's,
I don't like Julia. I consider like
no, yeah, he got through his tenure.
I just
promotion
got
and
my
everything.
tenure and I still consider myself a junior professor.
But it's still been years, right, since he had to get any advice from other faculty. So it is, and today in AI or any other areas of computer science, the amount of literature and publication is so fast that it is,
Do you have any advice how students do not get overwhelmed out of these like huge amount of publications? Do you have any insight to share with students?
No, so
Because sometimes I feel that they get overwhelmed out of like, I mean, every year, every day you look at like publication, Google Scholar or like archive, like just in ML AI, how's it? And this is
absolutely.
overwhelming, and I'm sure you have some insight to share.
Let me share what I have.
To have
Yeah,
them.
let me share what I have. I mean, we work in LLM and models, and that's massive amount of work going on, right? Here is deep sea comes and 1,000 people talk about that. So in my case, this bar is very hard for students to work with me and keep up with it. And that means, and I use various tools. So I have about 10 or 15 LinkedIn groups, and I every day share several of the materials for them to keep up with. If they look at the papers and videos that I share with them in their area, that research, they will be up to date. So I only do this lot of pre-screening through that process and give them kind of serve them just high quality, very relevant material. That is one thing we do. We have also the same number of Google Spaces. So strategic things on LinkedIn, groups and technical things of immediate interest, papers we are working on, updates, send the leaf link for the paper to be submitted. All of that is done on the Google Spaces. And there's lots of messages go on. So we try, they have to keep up to date, and that's hard, very hard. And then in our case, a lot of in-person time. So we have a student as a whole have Monday meeting, 10 o'clock, and we read a couple of papers, or there will be a dry run for one of the students. On Friday, we have group meeting for usually lasts 1.5 hours. In our case, we have about 20 students here, but there are number of students, interns working, online from other countries and participating. We had posted a internship, saying if anybody wants to intern, in 24 hours, there were 487 applications from the top places in the world. So there is such interest in people working with us. So it's very hard for us to pick the right students and keep up with them. I insist that even the interns join those meetings. So a lot of meetings. So in that meetings, there's all these updates that go on. And then there are project meetings. So typically we have maybe about 8 to 10 active projects going on, and student coordinators, leads. There's a faculty there, but then there is a student who is doing coordination, a senior PhD student or such, or very good medium level PhD student, and they would have meetings, and they will do that. So it comes down to building work culture. So Dr. Waltota, Walafa rather, made a comment in the last department meeting that the department is like a desert. And then Dr. Michael Hughes said, look at AI Institute. I recently got a photograph, this guy, Ranjit and Chaturangi, they are laughing and working at 10 p.m. He's sitting out in the sofa and working on the paper and all that. To have the interest, and energy to do that work. I myself slept under the desk while I was doing PhD in my lab. So to have that energy is very important. These days, what has happened is that COVID happened, and a lot of students got used to working from home and working from Starbucks, and they don't want to come to the office. I had a hard time, but now I managed to make it again all in person, because you can't replace brainstorming. You can't replace, particularly when you're doing creative work.
Yeah, that's very important. Yeah, brainstorming.
Yeah, so you have to have boards. You have to have, you will discuss in person, and there are many other things that I also work on. I work on not the research and research papers, but then communication, networking. Today, suddenly last 2 years, get jobs enough, it became very difficult. Before that, you know, I mean, my last PhD got an offer for 325K from Samsung Research, although he chose to go to a tier one research university as an academic. But then the jobs have dried down. How can you get set yourself apart? So I have a philosophy. It's called what is it that you have that others don't. I think I mentioned it in my first class, so I'm repeating myself. But those are the things you do. But essentially, forcing the people to engage, have the targets. And you saw I mentioned that Manas had more than 40 publications, but more importantly, more than 1,000 citations by the time he graduated. Kaushik Roy has more than 1,000 citations now. And last year he had maybe 20 publications or something.
And this is,
And some
if
of
you don't mind, I would like to highlight one important thing, which is doing academic. I mean, I consider Amit as my senior. He has like way more experience and way more order of magnitude, more publication. My style, and this is absolutely good to have different styles in academia, right?
absolutely.
My
absolutely.
style is different. I mean, and again, my style comes from my advisors and those who have been influencing my training, right? Where I am now, right? I just not become professor just out of sudden. I had multiple advisors, and I'm particular last place that I've been at Carnegie Mellon University. And mine come from like my advisor, right? Mostly my CME advisor, but also my PhD advisor to some extent, less, but like, I mean, like since I got inspiration, primarily my Carnegie Mellon University advisor, Christian Kastner, I like his style, also adopted his style. I mean, he has like citation, like look at citation, like huge. I mean, but citation, in my perspective, and also in his perspective, doesn't matter. And I believe in the same. And this is also good to have different style, right? Because I mean the style is different. Both are good, right? I believe in this diversity of style, and like many other awesome professor in our department have different style.
Yeah.
None of them is like me and I mean they look at a style differently, right? And these variation in different styles are awesome because some students are better matched for the style Amit has, and look at his group size, it's huge. I mean, like my group size is like the moment very small. I mean, size of my group has changed, but at the moment is very smaller. And this comes from like my preference. And again, you can have this variation, different style, and all good, all good. And having this diversity of style, that's why, I mean, we have best university, at least in the US, in the world, right? I mean, we have like good university in other places in Europe, but I mean, US is US because of has the best universities and come from this diversity of different style, and that's why it is giant universities are here, applying, doing awesome research and advancing the state of the art, comparing with like good decent universities in Europe, some of them like comparable to good universities, like top university here, but US has way more, right? Hopefully it makes sense.
I totally agree with everything you said. Only thing I'll add is that at the end of the day, student success is the most important criteria.
Yeah.
So not
totally.
citation, not anything, basically, and each student is different. Some, few wants to go to academia, it's very hard. Many go to industry, but only few can manage to get into industry research. You can get into develop more easily, testing, whatever. And then some want to be academic, entrepreneur. And that is a very demanding and very different kind of training. Understanding what students have, if they have high ambition, then they can all work and get, so the faculty advisor is role is to get them to succeed. Problem comes, failure is when student they can't get the career that for which they invested 5 years, 6 years in PhD. So that is where it is. That's why we have to make sure they understand their competition and what they need to have to get those jobs. In my case, if a student wants to go to academia, then I tell them what the real world is. At the end of the day, I can think whatever is the right, but the market decides, right?
Yeah.
So you have to know the market and how they make the selection and make sure our students can pass, that kind of stuff. Anyway, this you got.